Hi guys, so today we'll be discussing about Dfs Traversal in Iterative. So using iteration we can implement Dfs. As you have seen my previous video, I have discussed about Dfs Traversal using recursion. So in Dfs iteration, here what we do is instead of calling the same function again and again and using a recursion stack, we will now use a while loop which reduces Recursion stack space and gives us a better space complexity. So let me show you how it can be done with an example. So here, using this code, we'll be printing the nodes of this graph in DFS order by starting from the given source vertex using iteration. You can see that instead of calling the function, we will use a loop to visit all the nodes in the given graph and trace the Dfs traversal path. I'll be using stack variable, a visited variable, and the path variable, and I'll be telling you what is the use of all these variables. So why is stack used for DFS? In recursion, we have seen that in order to implement DFS, we use backtracking, right? From 1 to 2 to 4 to 6 to 7. When you reach a dead end, then you need to go back. That is called backtracking. Go back to the node which has some unvisited nodes or neighbors, right? So here we backtrack to 2 in order to reach the node 5. So for backtracking, we always use a stack. Hence, as DFS is nothing but backtracking algorithm, we will use stack. Next we have is the visited list. What is the use of visited list? Now what happens when we start visiting the nodes 1, then 2, then 4, then 6, then 7, and we go back to 2 then, right? So you see that 2 has neighbors 4 and 5. Now the program, if it does not use a visited list, then it will go to 4 and add this again to the path. But that time the path already has 4. So to avoid such cases, we use a visited list to check if the node we are encountering was visited before or not. So this is why we use visited list. Then path will store the final path of Dfs traversal. So I'll show how this is done step by step in the loop. First, the source node is 1, which gets added to the stack. Then once it is added to the stack and we are visiting it, we change the visited list for index 1 to 1. That means now 1 is visited and we need not visit it again. So first in node, we pop the first element of the stack and we add this node to the path. Then for neighbor in graph of node, the neighbor of 1 is 2 and 3. So now 2, if 2 is not visited, here 2 is not visited, right? Because the value of visited of 2 is 0. So it's not visited. Therefore, visited neighbor change 0 to 1. Now 2 is visited and this is appended to the stack. Next in the for loop we have 3. Now 3 is not visited, right? Therefore, now node 3 is also visited and we add it to the stack. See here, this is not getting added to the path. That gets added outside this for loop here. So now we are only adding it to the stack because we have to traverse these two nodes in depth. I'll show you how that works. So now for loop is done. We go out and we see that stack has elements. So now the topmost element is again popped. Now my node is 3 and my path has 3 gets added. Now for neighbors of 3. Neighbors of 3 are 5. So we check if 5 was visited before. It wasn't. So we make it 1 in the visited list and 5 is added to the stack. We go back to the loop and we check. We pop the topmost element. Now the topmost element is 5, not 2. Here 5 is our next node. It's popped out and it is added to the path. And it is my current node as well. So we check for the neighbors of 5, which is 6. So here we check 6 is not visited. Let's visit it. And we add 6. Now stack topmost element is 6. So the topmost element is popped. My node is 6 now. It is added to the path. Now we check for the neighbors of 6, which is 7. So is 7 visited? No. So we visit it and 7 is appended to the stack. Now we go back and we pop the topmost element, which is 7, which is my node now. Okay. And 7 is added to the path. Now you check if 7 has any neighbor. It does not have. This loop won't be executed. And now we go back and check the next top element of the stack, which is yet to be visited, 2. So now node is 2 and path has 2 added here. Now for neighbor of 2. Neighbor of 2 is 4 and 5. 4 and 5 are the neighbors. We check if 4 is visited. 4 is not visited. So we can visit it now. And stack has 4 being added here. And next is 5. Is 5 visited? Yes, it is visited. So the loop breaks right here. And we go and check the stack again. Now in stack we have 4. It is popped out. Okay. And this is added to the path. Now we check for the neighbors of 4, which is 6. Is 6 visited? Yes, it is. Therefore, now the stack is also empty. And we have a path for Dfs Traversal here. Therefore, you can see that all the nodes are visited and nodes were not repeated due to the visited list. So the next step after implementing the code is to evaluate the time and space complexity. The time complexity here will be big O of E plus V, which remains the same because we will be visiting the total number of edges and vertices, right? So it is the addition of edges plus vertices, that is the time complexity. Space complexity will be big O of vertices because we have two spaces, that is one is path variable and visited variable and the stack. So cumulatively we are visiting the nodes and it will be big O of 3n. And lastly, let n be the nodes, which is vertices. So this equals to big O of n only. So this is the space complexity. And the space complexity is better than the recursion of DFS because we do not use a recursion stack here. Therefore, this was the iterative solution of DFS. So guys, I hope you understood DFS using iteration. That's all. Thank you.